Hi, everyone. Thank you very much for the introduction. For those of you watching right now on the live stream, I applaud your mental capacity to join a security conference on a day like today. If you're just watching a recording of this video, congratulations. That means you survived these times, so good for you. Kudos. If you're watching this far in the future and don't know what I'm talking about, just Google 2020 and it will explain everything. My name is Arthur. I'm an engineer on the Google security team. I also manage a team of about a dozen security and software engineers that work primarily on web security at Google. So as you know, Google has thousands of applications, and they're written using many languages, many serving stacks, and it is very important for Google, for the web platform itself, to be secure so that it can form kind of a safe basis for our applications. The topic that I have prepared for today is something that has been many years in the making. I've been really excited about the ability to talk about this because it's the first time that we get a chance to delve really deeply into the question of isolation on the web. So let me set it up a little bit and give you an idea of what we will talk about today. This is a very technical talk, but it's not uniformly complex. So specifically, what I wanted to do is first start a little slowly, give you a little bit of an idea of what the space that we're working on is, then tell you a little bit about new web security features that you'll be able to adopt in your web applications. And then towards the end, it gets kind of gnarly and there are a couple of features that are difficult conceptually, but afterwards, if I manage to do a good job delivering this talk, things should make more sense. So let's get started. This image, I was trying to think of a good image that would kind of encapsulate this talk, and this image is called the pale blue dot. It's a photo taken by the Voyager 1 in the early 1990s. It's a photo of Earth from 6 billion kilometers away. So it's essentially the best selfie, the farthest away selfie that we've managed to take. And there are two reasons why I chose this image. The first one is this talk is about isolation, and I don't think there's anything else that portrays isolation as well as this photo. The second reason I wanted to show this image is that what I will talk about today is a very exciting area of security, but it is really just a tiny sliver of what an application security engineer these days has to understand and has to work with. So we will go very deeply into this technical topic, but I also wanted to acknowledge that there are many things that many of us are doing that make this particular area, just one of the many that we need to deal with. So before we get there, I wanted to also maybe disambiguate what isolation means in the context of my talk. Because this was my concern when I was thinking about the title. Isolation is such an overloaded term that there are many ways to interpret it without really understanding what this talk will be about. So I'll give you a bit of a preview of what this talk is not about, and then we will slowly start getting into the real technical details. So let's get started. So you can think about various areas of security that have an isolation component, such as network security and firewalling. This talk is not about that. It's also not about isolation at the operating system level, like Kubernetes containers. So if you saw isolation and you thought you would dial into this talk and you'd learn something about Kubernetes, I have to disappoint you. I'm not going to talk about this. Similarly, there is virtual machines and various things you can do to improve endpoint security at your company. Not that either. Finally, there are there's build tooling and isolated build environments that you can use to make sure that you build your applications verifiably. And this talk is not about that either. What this talk is about is isolation in the context of application security, but I'll be even more specific. So this talk is not about either mobile app security or low-level security, memory corruption, and these client-side issues that have been plaguing our ecosystem for decades. This talk is about web application security. And it's even more specific than that. It's not about server-side security, so attacks that can be executed directly against your infrastructure to execute code or inject SQL queries and so on. Rather, this talk will focus on client-side security. So client-side web application security is protecting our users, so users who are logged into our web applications, from vulnerabilities that could be exploited by other websites when the user is logged into our application. So the mental model that you can operate under here is that someone has one tab in which they are logged into your application, and they have multiple tabs to other sites that may not be trustworthy at all. And of course, this is not the only setting in which these issues matter. The same things apply to WebView, Electron apps, mobile web apps to some extent, but it's easiest to just think about this as a user having a browser open and being logged into your site. And finally, I will make this even more precise. So I'm not going to, obviously, I cannot cover all of client-side web application security in one talk. I just want to focus on one of the three major elements that make up client-side web security. So this is a fairly opinionated view, I will admit, but I will claim that client-side web security has only three major issues, three major problems. The first one is the fact that you can have an application that uses insecure transport, so HTTP, forgetting to set a secure cookie. This is one kind of big source of problems that we've historically had on the web, because if you don't use a secure transport, that means all the data that you have in your application can be intercepted by someone on the user's network. The second big area of client-side security that I also won't go into details about, but there is a link in the slides please feel free to check out if you want to learn more about this, is the area of cross-site scripting, which arises primarily because the web lacks a separation between code and data. But finally, the third biggest, let's say, pillar of web insecurity, if I may call it that, is the fact that the web is missing isolation between various web applications that the user has open at the same time. And this is what I will focus on for the remainder of my talk. And I will try to make a case for the fact that this is a really important class of vulnerabilities that we haven't really thought about much as a cohesive class of issues. And I'll make a case that it really is one class of issues, and that we should build and deploy mechanisms that address this class of issues in our applications. So after a long journey from 6 billion kilometers away to our planet, we finally narrowed down what this talk is about. It's about isolation within web applications. So let's say that you have a bug bounty program, and you get a report from a researcher saying your application is missing isolation. What does that mean? This doesn't carry any real meaning unless you clarify what exactly the lack of isolation leads to, what exactly the security problem is. So let me give you a few quick examples, and I won't go into a lot of detail, but quick examples of different security issues that most of us working on web security are familiar with, each of which has its own acronym, but all of which can be seen as violations of web isolation. So most of us are familiar with issues like cross-site request forgery, clickjacking, cross-site script inclusion, also known as JSON hijacking or JavaScript hijacking, and some variants of cross-site leaks. All of these are issues in web applications that are easy for developers to introduce if they're not very careful. All of them have slightly different mechanics of what the pattern is that is vulnerable and how it is exploited. But what all of them have in common is that there is a part of your web application that does something that is seemingly safe or not suspicious in any way, at least for non-web security experts, but that leads to some information leak or some security problem. And the thing that all of these vulnerabilities have in common is that they are based on the fact that an attacker can send a request to your application or open a window to your application, which will, when a request is made or when a window is opened, the browser, the user's browser, will send cookies alongside the request, will send cookies alongside the request to open a new browser window. And the fact that these requests are all authenticated is what is the underlying factor for all of these various vulnerabilities. So these are the specific ways in which an evil website can exploit each of these issues. So essentially, there's some markup or some code on another site that will result in information leakage or an unwanted action being taken by your application. And they are fairly straightforward to exploit by another website. So let's try to think about this not as individual classes of security issues, but rather as one underlying problem with the web. And what I will claim is that the problem with the underlying problem with the web is that it wasn't meant as an application ecosystem. It was meant as a way to have documents that would hyperlink to other documents and organize information this way. And it was a great vision, but the web is so versatile and so powerful that in the 30 years since the web was proposed, it acquired so many features that enable us to build web applications. But the downside of this is that, of course, we have to deal with the fact that we are building web applications upon a system that wasn't meant as an application delivery platform. So one example, and this is something that I never really thought about, but all the features that our applications use today to allow users to log in, have a safe experience, safe state, just make users happy, all of these features like encryption or maintaining state client side or the ability to execute scripts or even a fundamental security feature like the same origin policy, they didn't exist when the web was conceived of. In the first few versions of major web browsers like Mosaic or Netscape, none of these things were implemented. These features were added later in order to make the web an application platform, but they were kind of retrofitted onto what had existed before. And specifically, if we think about the two particular features that result in these isolation concerns, it's the fact that anytime you send a request to another website, the browser will attach your cookies from that website, which means that an arbitrary external site can send a request that looks exactly like a request that would be sent by your own website. And the second thing is, kind of by design, every resource on the web, or most resources on the web, have an address, right? They have a URL. So that makes it easy for another website to just target a specific bit of functionality in your platform because they know the address and they can send a request that will carry the user's authentication credentials. So this results in a very large attack surface that most other application platforms do not have. And it also results in all these vulnerability classes. So we have to do something about this in order to make the web a safe application platform in the future. So this was the background. I know it was a lot of backstory, but now let's get into the exciting part, which is the new security features that can help you protect your web applications from some of these endemic isolation bypasses on the web. So what we have to do is design mechanisms that will address the various bypasses of isolation in a principled, robust way. And what this looks like in practice is that we have to implement isolation in the web platform and adopt these mechanisms in our applications at 3 different levels. So the first level is we have to allow websites to protect their resources from being loaded directly by an attacker's document. Have some way of letting the application say, oh no, I don't want to deliver my resource to an evil website. The second thing we have to do is we have to protect windows. So, think about a pop-up or an iframe or a window from tampering by other websites. Currently, there's very little that you can do to break the linkage between a website that opens you and yourself. So we have to build mechanisms that achieve that isolation. And finally, and this is the most surprising part, and this is where most of the complexity here shows up, is we have to allow applications to opt into process isolation so that they're not part of the same operating system level process as an attacker's document. And we'll get into the details of that. There's some other things that the web platform needs to do to really, let's say, realize the isolation guarantee, but that we can leave that for later. This is something that web developers don't really need to think about a lot. And this talk really is about how, as an application owner, you can get these guarantees from the platform. So let's start with the first type of isolation. So how do you make sure that the resources that your application serves, like images or scripts or HTML, cannot be directly accessed or cannot be requested by a website that you don't trust. And this is the fact that you can do this today results in many of the vulnerability classes that we as web security practitioners are familiar with, that you saw a couple of slides ago. So what can we do against this? First, there are some things that the browsers already do by default. So, for example, cross-origin resource sharing has built-in logic that prevents you from sending cross-origin requests and set custom headers, right? This is just not allowed by the platform. So there are some restrictions there. Some browsers also implement other security mechanisms, such as Safari. One of the recent versions of Safari stopped sending credentials, so cookies, on cross-site resource loads. Chrome has moved a few months ago to same-site lax cookies, which also reduced the number of credentials that are sent on cross-site requests. But this is not enough from a security point of view. This is great, a great start, but these default features are not sufficient to protect your application from most of the attacks that we talked about. So what we need to do to complement these default features are opt-in security mechanisms that we as developers of sensitive websites can enable to protect them. So specifically, the two mechanisms that I'll talk about today are fetch metadata request headers and the cross-origin resource policy. So let's move on to fetch metadata request headers. This is a really simple conceptually feature that is very powerful and that lets you implement very robust and very elaborate security logic on your server to protect you from various kinds of isolation bypasses. So how does it work? In a nutshell, web browsers start setting 4 different request headers on every HTTPS request. Those request headers, like segfetch site, segfetch mode, and so on, give the server some security-relevant metadata that the server can use to decide whether to accept a given request and return a response or to reject it. And these values, they're not arbitrary. They map directly to what the fetch specification defines. So if you look to the right side of the slide, this is just an example. If you are example.org, you load an image, the values of the segfetch headers will tell the server when the request is made that this is a same origin request that is used as a sub-resource and that will be used as an image. Whereas if you make the request to the same URL from, let's say, evil.com, the server, your server, will know that this is a cross-site request that has different properties. And based on the distinction that the browser allows you to make between these requests, you can implement security logic that will protect you from many kinds of isolation bypasses. So let me show you a very quick example of what middleware could look like to protect from, for example, cross-site request forgery, cross-site script inclusion, and related bugs. So here, it's just a set of a few very simple conditions. So first of all, you have to be backwards compatible and allow requests that don't set the header, so that browsers that don't implement the specification yet don't break when users use your site. The second thing is you can look at the source of the request. And if the source is trusted, so if the request is same origin or same site, you allow it. And finally, if the source of the request is not same origin or same site, so it's a cross-origin request, you can allow only navigations, but not sub-resource loads. And there is more to it. There are links that explain each of these conditions, but this is an example of the logic that you can implement to give your site resource-level isolation. You can do much more with fetch metadata request headers. For example, you can even restrict navigations. So you can prevent other websites from directly linking to your renderable documents and only allow navigations to a set of allow listed endpoints that should accept navigations from the outside. But I won't go into the details here in the interest of time. So this is a really simple but really powerful mechanism that lets you get a lot of security guarantees that weren't possible before. Here are some tips for deploying it. The first thing is that because this is just a set of request headers, servers can check whether deploying fetch metadata security logic would result in any breakage, because they can come up with logic like this in the slides before and see how many requests would be rejected and decide that they need to refactor something in order to prevent that breakage. The second thing is there are some response headers that you have to set just to get full protection. I won't go into the details of that. And finally, and this is a tip based on deploying this logic across hundreds of applications at Google, you will, if you have a popular web application, you will see a lot of requests that seem illegitimate or bogus. So any site on the internet can load an image, can, let's say, hotlink to an image on your site, or load an image as an iframe, or do things that you just don't expect. So don't be afraid to break that. In many cases, we have done this. We weren't sure if this would result in any application issues, and we've had fairly good luck so far. This hasn't caused any breakage. So if you see a small amount of traffic that seems like it would be incompatible with these security rules, you can try to break it and see what happens. There's a great article written by my colleague Lukas Weichselbaum that you should read for more concrete tips. Okay, let's go to the second mechanism. Client-side, so browser-side complement to fetch metadata request headers is the cross-origin resource policy. This header works almost exactly like X-frame options, except that it applies to sub-resources, so images, scripts, style sheets, rather than iframes. It has three fairly self-explanatory values, so same origin, same site, or cross-origin. And the browser inspects that header when it tries to load a resource. And if the relationship between the requester of the resource and the server that responds with the resource doesn't match what the header says, then the browser will prevent that resource from loading. So this is, let's say, simpler conceptually because you can just set a header. You don't have to have server-side logic, but it also gives you fewer security protections, because by the time you make that check in the browser, the server has already processed the request. So attacks like cross-site request forgery or timing attacks would not be stopped by this, because the response looks almost exactly the same with the header and without. And another issue here is that cross-origin resource policy doesn't make it very easy to know what will break if you set the header, so fetch metadata can help with that. But what you can do to get the full benefit of the cross-origin resource policy is to use it in combination with fetch metadata. So what we have done internally across Google is we check the sec fetch headers that are part of fetch metadata, and based on the values of these headers, we set the cross-origin resource policy. There's some more complicated logic there, but you can use these two mechanisms to reinforce one another. There's a great website that tells you a little more about cross-origin resource policy, but I will refer you to that to learn more. Okay, so we're done with the first level of isolation, resource-based isolation. Let's talk about the second kind of isolation, which is window-level isolation. So it was always a surprise to me that if you are an evil website and you open a window to another web application to which the user is logged in, you have free rein to do a bunch of things that seem unexpected to the application developer or to the user. So for example, if you open another window, you can always send messages to it via post message. You can traverse its frames and know how many iframes are in that window, even if that window is a cross-origin window that you shouldn't have any access to. And you can also redirect it, navigate that window to an arbitrary URL. And this results in several classes of issues like tab nabbing, various kinds of cross-site leaks, and it's just, let's say, a bad idea as far as web platform security is concerned. So, and up until very recently, there was nothing that you could do as an application developer to prevent another website from interacting with you in this way. So the only saving grace was that the same origin policy prohibits direct accesses to most properties of your window from a cross-origin window, right? So another window cannot look at the data you have in your window, but it can still access your frames, history, redirect you, and so on. The main new security mechanism that fixes all of that is the cross-origin opener policy. What the cross-origin opener policy does is it lets you decide that the link from the opening window will be broken based on the relationship between your origin and the origin of your opener. So this applies only to top-level windows. So it has to be used in combination with X-frame options, but it's still a very powerful and relatively simple mechanism. That mechanism has three different values. You can set the cross-origin opener policy header to unsafe none, which is the status quo, what we have today in the platform, so no protections. You can set it to same origin allow pop-ups. This is helpful if you want to be able to open pop-ups and communicate with them, but you don't want someone who opens you as a pop-up to get a reference to you. So it's unidirectional protection for your window reference. And finally, the best mode here from a security point of view is cross-origin opener policy same origin, which will break the association in both directions. This security mechanism comes with its own report-only header, so you can check for compatibility, deploy this, see what might possibly break, and then fix your application if need be. And one other caveat here is if you have flows in your web application that require communicating with a cross-origin window, OAuth is one common example, you may need to set co-op to same origin allow pop-ups instead of same origin. And we have two really interesting articles that talk about the details of that. All right, so we are done with most of the talk, but we still have one large, complex area that I want to tell you about today. And this is the most surprising and challenging to fix from the web platform's perspective. And that is, we talked about the two levels of isolation for resources and isolation at the window level. So now we have to talk about isolation at the process level. The reason we have to talk about isolation at the process level is that since early 2018, we as a community have been aware of a class of attacks that allow code executing in a renderer process to read data in its own address space, so read its own memory, even if it otherwise wouldn't be possible due to web security rules. So it's essentially an attack at a lower layer of the security stack. Spectre and Meltdown are two examples. There have been, I think, by now a couple of dozen of different attacks that work in the same way. So this is one class of issues that we have to grapple with here. The second class of issues is that browsers have bugs, right? If you're a complex piece of software like Chrome or Safari or Firefox, your renderer will have memory corruption bugs, will have other kinds of issues that allow an attacker to potentially execute code within the renderer process. Because of sandboxing in most browsers, this is still not full system compromise, but if someone executes code in a web renderer, then they can similarly execute these attacks. So, yes, this is the reality that we have to live with. But if you think about this, this is really wild because we as web developers have never really had to care about what the browser's process allocation model is, right? The web is the web. It's at a higher level than operating system processes. So why do we really need to suddenly think about this and take it into account when building websites? There's a very specific practical reason for this. When Chrome developers have analyzed these classes of issues a couple of years ago, they realized that because of the CPU level issues that I mentioned a couple of slides ago, it is practically very difficult for the browser to be able to separate different security principles that exist in the same operating system level process. So what we have to do instead is to use process separation as the security boundary, because if we exist within the same process as attacker controlled code, there's very little that the browser can do to protect our data. Something that is also worth pointing out is that there are these days reliable exploits for Spectre and related bugs written in JavaScript. So this is only going to get worse from a security point of view. And the problem is that neither CPU vendors nor browsers can fix that by default because doing so would it's just very hard. From the browser's point of view, it requires web-level changes. From the CPU vendor's point of view, it's just impossible to update CPUs in this way to protect from these bugs. So this is a problem that has, let's say, reached the web layer, and we have to figure out how to address this. There are things that browsers are already doing by default. So I'm sure you've heard about site isolation in Chrome. Other browsers have similar features in various stages of implementation. But when we're building a sensitive website, we have to do more. We have to use some opt-in security mechanisms to complement the default protection that browsers give us. So this is where we get into the area of cross-origin isolation. What we can do what the web platform has to do is provide us a mode where the browser can guarantee that you are living in a separate process from cross-origin content, and all the resources that you are loading opt into being loaded. If the browser can assure you of that, it can also change the process allocation and segregate your application, put it in a separate process. And this is really great for security. And the good news is that if you adopt cross-origin opener policy, you already are well on your way to making use of this process isolation benefit. The bad news is there is one final mechanism that we have to talk about. That mechanism is called cross-origin embedder policy. That mechanism, if you set that header, right, if you are a website that sets the cross-origin embedder policy header, there's just one value, require corp. The browser will ensure that only resources that have explicitly opted in can be loaded by your document. Resources can opt in either via CrossOrigin resource policy that we talked about before, or traditionally via CORS. And this constrains you in some ways, but it also lets the browser guarantee that you only have access, you cannot load any resources that didn't opt in. So, in a nutshell, I know this is a very complex area, but we can make it simple. So, if you're a developer, if you set the CrossOrigin opener policy and the CrossOrigin embedder policy, the browser knows that you don't direct with other CrossOrigin windows directly via window references, and knows you are not embedding CrossOrigin resources that don't opt in. And that can give you security, so process level allocation, and it also lets the browser expose functionality to your window, to your document, that otherwise wouldn't be safe to expose in the web platform. So in the interest of time, I will also skip this section. There are really great articles that tell you more about it. There is one complementary mechanism that I'm happy to chat about if anyone has questions, but I will move to a summary just so to maybe make this whole bundle of security mechanisms clearer. So if you're a web developer, right, you've listened to this talk, it all seems so complex. What do you actually need to do to protect your web application? It's really not as complex as it seems. In order to get isolation at the resource level, you can use fetch metadata request headers that browsers are attaching, complemented with CrossOrigin resource policy, and that will give you resource level isolation. If you want to isolate, protect your window reference, you can set the CrossOrigin opener policy header and complement this with X-frame options to prevent embedding by untrusted sites. If you additionally want isolation at the process level, in addition to CrossOrigin opener policy, you have to set CrossOrigin embedder policy. And these articles on the right tell you a little bit more about that. If you do this, right, it seems like a lot of work, but if you do this, you gain really major benefits for your application. The first thing you gain is you gain security. These mechanisms act as a defense in depth for known classic types of web bugs like cross-site request forgery and so on, and also give you a defense mechanism against new classes of attacks that haven't even been discovered yet. It also gives you a reduction in the attack surface. So implementing these mechanisms from the previous slide gives you the three types of isolation that we were after in the web platform. Additionally, if you do this, the browser will be able to expose features that it otherwise couldn't safely expose to you, like the ability to see how much memory you're using, and other interesting APIs in the future. And finally, websites will move to lock down these defaults to make them safer. So if you implement these mechanisms, you will be ahead of the curve and will not have to scramble to refactor and add these mechanisms later. My one final thought that I will leave you with is it's the second question on this slide. This seems like it's complex, right? It's many different mechanisms that may require refactoring your website. But if you look at each mechanism on its own, these mechanisms are actually fairly simple. So fetch metadata is just a simple set of request headers. CrossOrigin resource policy has just a couple of values. The complexity that we have to deal with arises from the interplay between web applications and the process model, which is inherently complex, and we cannot get around that. But the effort that we have to put into understanding these mechanisms also translates into very real security benefits for our applications. So I would encourage you to learn more about these mechanisms. It's a very interesting area. We are at the end of our talk, and I think I took a couple of minutes more than I meant to. So I will see if we have any time for questions.
Arthur, you did an amazing job. We definitely have time for questions here. I mean, one of the benefits of being virtual is that, it's really on us, right? Some of the physical things here. But thank you very much for the talk. We do have some questions, and one I think is going to be around just kind of like the organization that you're with, Google, and that you guys have one of the leading browsers in this space. It sounds like a lot of the things you're offering interact with the browser. You touched on it a little bit, but what can we expect to see from Chrome, or as much as you can tell us, in being able to help support these safe defaults?
This is a great question. So it would be great for everyone, for users, for web developers, and for the platform itself, if these features could be enabled by the platform by default, right? So as a developer, I don't necessarily want to have to know about cross-origin opener policy or cross-origin resource policy and these mechanisms. The difficulty is that the browser, if it wants to enforce these restrictions, introduces a large potential for breakage of existing websites. We've seen this a little bit with the Same Site Lacks by Default launch. The Chrome team has done an amazing job in trying to move to a safer default for cookies, but it did take a lot of time, work with many application developers to ensure that users keep being able to use websites that they have been using for years, right? Not every developer has the resources to update their website so much. So we have to, the trade-off that we have to deal with is, on one hand, safe defaults are great. On the other hand, there is breakage potential. A colleague of mine, Mike West, who works on the Chrome team and builds the specifications and implementations for many of these features, has put together a great document that talks about how the web could move towards pretty much all the mechanisms that we discussed in this talk by default. But the way it will happen will be very gradual and will take many, many years. So there are plans to do so. However, for the purposes of, let's say, for our community, right, for the folks that are on the live stream that are watching this talk, it's very likely that you are an application developer or a security engineer working with a web application. In practice, what we have to do in the short term is deploy these mechanisms on an opt-in basis. And then we can hope that over time, the web application behaviors will move to a state where browsers can start ratcheting up these restrictions to make the web safe by default. But until then, just use the opt-in mechanisms.
Okay. Next question, I think we tied into it very nicely. What is Google's adoption rate for these protection mechanisms? And are you planning to implement them for all web applications? The latter half, I think you've kind of addressed, but what is Google's adoption rate for these protection mechanisms?
Oh, this is a great question. I love to talk about this because this is what our team does. We are very actively working on deploying all of these mechanisms across our ecosystem. Google is a very diverse set of applications, so we do it piecemeal. We target, for example, one framework, and we gradually roll out fetch metadata restrictions, cross-origin opener policy. There are some applications, some popular applications used by millions of users today that set all these headers already. But judging from our experience with content security policy, on which we have worked for several years, and we are up to, I think now, about 70 to 75% adoption in our ecosystem, the rollout of all these isolation features will also not be something that we can just flip a switch and enable for all of our applications, but will take quarters, if not years.
Okay. And then another question for you. Who is responsible for implementing mechanisms like these at Google? Is it the web developers? Is it security engineers? And what does that look like in terms of why one team would own it versus another?
So this is a little Google specific. At Google, the information security engineering team tries to do a lot of the heavy lifting for these features. So for example, we write the documentation, we build the implementations and integrations of these features into our frameworks. And in many cases, we also help product teams with the rollouts. So for at least a subset of our applications, we try to do this so that the product team doesn't have to do a lot of work to enable these features. However, there are two things to keep in mind. One is that our team is a fairly sizable application security team. I don't think many other companies have the benefit of having so many people that can solve these problems for regular developers, right? So it may not be as easy at your company. The second thing is that there's definitely a long tail of applications at Google that use maybe custom frameworks that are a little more difficult to work with, and there we rely more and more on developers to do these integrations. So there's a spectrum of let's say effort that you have to be prepared to do. If you use one of the modern new frameworks, we handle most of the work, most of the security work for you. If you use, let's say, a legacy framework, we may prepare documentation and we may file a bug for you explaining what you have to do, but then you are kind of on your own. And both of these approaches are successful to some extent, but this is very specific to what kind of application it is, and probably different organizations will have a different model for these rollouts.